Okay, so we've already looked at beams to some extent. We've looked at normal stress in bending, so using the equation stress equals my upon I, and we'll look at that again in a second. We've looked at shear stress, and we've also last week looked at deflection. So in this lecture, we'll bring those things together. All right, so usually when we're designing a beam or a beam-like structure to carry a load, we usually do that on the basis of strength. Okay, so we want to know that the beam is able to carry the internal shear and bending moments that are required by the loads that are placed on it. Oops. But we also need to design according to stiffness. So often you'll see a beam or a beam-like structure that will deflect quite a lot, but it's not close to breaking, right? So I've said to you before that strength and stiffness or rigidity are two different things. They're related, but they're not the same. Okay, so you can have something that will deflect quite a lot. So if I grab my stick here and I put a load in the middle, I can bend that quite a long way, right? And you may know from walking across some light bridges, suspension rope bridges and stuff like that, they can bend a bit, but doesn't feel very safe, right? So often the stiffness requirement or the amount of deflection that you want to limit to overrides the strength requirement. So usually if it's stiff enough, it'll be strong enough, but obviously you need to check. And if you've got any questions or comment, please jump in and ask at any time. All right. And then the other thing that we need to be aware of when designing beams is buckling. And buckling is an instability failure. So we won't do any buckling in this subject. When you go on to do, or if you go on to do Applied Mechanics and Design B, then you'll look at buckling there. But if we have a beam that's this kind of shape and we put a load on it, it can sort of have out of plane deflection, right? You probably may not be able to see that very well, but you get lateral deflection due to a kind of buckling, right? But we won't deal with that in this subject. That's just a note, I guess. And then in practice, if you're designing something for a building, probably not as a mechanical engineer, but maybe if you're building a crane, a workshop crane, and you've got the gantry that goes overhead and the winch, that's something you may do as a mechanical engineer. You'll need to make sure that your design meets the code requirements. And in Australia, that code for steel structures is AS 4100. All right, so we've seen these two formula before. Hopefully you're up to that part of the subject by now, where we've looked at calculating the normal stress due to bending and also the shear stress due to bending. Okay, so if we have a beam like we can see here, we've got some loads applied to it, we'll get normal stresses developed and we'll get shear stresses. Okay, and these are our two formulae that we use to calculate what those stresses are. And then in design, we'll say, okay, these are the stresses we've got. How do they compare with the allowable stresses? So the other thing to note when we're doing beam design, if we've got a load applied like this in our textbook problem, right, you know that there is no arrow with a P sitting next to it on the real structure. There's some physical thing here attached to this beam that's generating this load. Right? So as part of your future development as engineers, you need to think about, well, can I, if I have a beam like the paddle pop stick here and I push down in the middle with my finger, right, that load is distributed over the area of contact between my finger and the beam. Now you could model that as a point load like we've done in the PowerPoint here, or you can model it as a small distributed load over a small area. Now, whether you do it one way or the other, what will happen is you'll get stresses developed underneath that loading point, okay, which are not calculated by these two formulae. Right? But usually we can ignore those. In some cases, there'll be standards. So there's if there's another piece of structure attached here, the standard might tell you how to transmit the load across, whether you can apply it as a point load or whether you can apply it as a distributed load. But for now, we're going to keep it pretty simple, but just be aware that what we're looking at here is quite a simplified approach, and you'll need to build on this basic understanding to actually go out there and design beams in practice. In the last few weeks, I've asked you in doing the tutorial problems to sketch the stress distribution. It's good to know how the stresses vary throughout the beam, especially if you're going on to do finite element analysis and structural simulation using finite element method, to be able to look at a solution and say, no, that doesn't look right, there's something wrong there. And that ability comes from knowing how the stresses should vary through the cross section. Okay, so the normal stress from bending, as we've seen, varies from 0 at the neutral axis out to a maximum at the outer fibre, and the variation is linear from the neutral axis to the outer fibre. So this is for stress equals my upon I, your normal stress due to bending, and then your shear stress distribution for a rectangular cross section is parabolic like this, with the maximum at the neutral axis or the centroid. Now, this is not always the case. When you go through the tutorial problems, if you haven't done them already, I've thrown in a couple of examples where it shows you that in shear, the maximum shear stress doesn't always occur at the centroid. Right? So you need to be careful. The part on the right here is looking at principal stresses and how stresses vary as we look at the stresses upon different orientations. So you don't need to worry about this for this subject, but just be aware where we have here, for example, part way through the beam, so not right at the top and not at the centroid, we've got combined stresses. So we'll have a normal stress, something less than the maximum, and a shear stress, something less than the maximum. Okay, so there's a combined stress here. So it's equivalent to, if you're thinking about forces, you have a resultant force, and then you have the two components, right? Force in the X, force in the Y. Right? Here, what we're seeing is the stress components. So we have a normal stress component and a shear stress component. And we can change the orientation, or if that's our force, change the orientation of our coordinate system. Right? So if the paddle pop sticks the force and my fingers are the coordinate system, we change the orientation of the coordinate system and the components change magnitude, right? So if we had two components like this, we can find a resultant, or if we have two components like this, we can find a resultant. This is what we've done here with stress, right? We've got normal stress component and shear stress component, and then we get the principal stresses at a particular orientation. So that is equivalent to, right, here's my actual force, the paddle pop stick, and my coordinate system is aligned along the line of the resultant force. Okay, so that's kind of the analogy that we're looking at here. Now, stress is not a vector, stress is a tensor quantity, so it becomes a little bit more tricky, and we have to use Moore's circle, which you'll see in applied mechanics and design B, and maybe in your design subjects, your studio design subjects. Okay. Haven't got my animations quite worked out for this slide, not to worry. So for strength, we need to keep the stresses below the normal and shear stress limit. And for stiffness, we need to keep the deflection below an allowable limit. Okay, so usually we'll start by looking at the strength requirement using this equation, right? Your beam flexure equation, stress equals my or mc upon I. And then we'll check the shear stress, and then also check the amount of deflection that we get. Now, often what we do when we're doing beam design is to not directly use the moment of inertia and the depth of the beam, because we don't know what the depth of the beam is. All right, so we'll use this section modulus. Okay, so the section modulus is just the moment of inertia divided by the distance from, excuse me, my throat is still croaky after all this time. So the moment of inertia over the distance from the neutral axis or the centroid to the outer fibre. Okay, so that's our section modulus, and then turning our flexure equation into a design equation, just rearrange this so that we have this required section modulus for a given maximum moment. So we did our bending moment diagrams a few weeks ago to work out where the maximum bending moment was. Now, if we choose a material and we have an allowable normal stress, we can design or choose a beam section to meet these strength requirements. Right, so the way we generally do that is to look up handbooks that have lists of standard beam shapes and sizes that you can choose from. Right, so an example here taken from your textbook. Excuse me, I'm going to have a bit of a drink and see if I can clear this croak in my throat. Okay, so here we've got American Institute of Steel construction standard, and we have a wide flange beam. So as you probably know, oh, excuse me, from just general knowledge or from intro to mech or whatever, you know, an I-beam is quite commonly used in beam construction and in structural design in general, because they're weight efficient. Okay, we have the stresses all being carried through the flange here. Okay, so you know, if we go back over here, right, moment of inertia is integral of ay squared. Okay, so what y being the distance from the neutral axis or from an axis. So the further we get the material away from the neutral axis, the larger our moment of inertia is, and so therefore the lower our stress will be. Okay. Okay, and the designations in the different tables, you just need to look up what they are. So for a wide flange beam, the first number gives us approximately the height of the beam, and then the second number is approximately the weight per metre. No questions yet? Okay, so the other thing that I put in, so this is from your textbook. If you don't have the textbook, or if you no longer have access to it through the library, so you all have access to the textbook through the UTS library, and there's, as you should know, there's links on virtually every page of Canvas that take you to the relevant sections in the textbook. But if you don't have that, you can go to these online tools. So this one's just one of the first ones I found. It's quite good. Go here. Oh, my hyperlink's not working. Anyway, it's in my slides. So yeah, just go to that URL, click on the one you want. What's happened here? I crashed. PowerPoint might have crashed. Oh, there we go. All right, so if you click on the one you want here, it gives you all of the section properties. All right. Now this from One Steel, so Australia, so Australian produced products. You go to their table and you can look up. So let's say you do your calculations, you can go and look up the section modulus that's required from this table. And all right, so in my notes, and I took those from the textbook, we're looking for the section modulus, which is denoted capital S, right? And the section modulus about the x-axis. Right, so we saw that the section modulus is I over C, and in this case, C will be D over 2. Right. If we choose a particular section, so here I've just chosen this one here, 315, moment of inertia is 277. D is 315. So if we do this calculation, we find out that the section modulus is actually underneath the Z column. Right? So you need to be very careful about using tables without thinking about, well, you need to think about and check what the symbols mean, right? So here, the section modulus that we want is actually the Z one, not the S. Right, so here, looking up and using another online resource, so Mechanic Calc, if you haven't come across this before, this is quite a good resource as well. So here we've got our section modulus. They've called it S, the same as I did in my notes. But if you go to this One Steel catalog, if you use S, right, you get the wrong one. So in this table, this S is actually the plastic section modulus, which you may come across in Applied Mechanics and Design B. So this is when you look at loading the beam beyond the yield limit. So you start to get plastic deformation. Okay, so this is actually the plastic modulus. So the main point is, understand what you're doing, understand the basics properly, and check what things mean before you use them. Oh, and this is just that same catalogue that I was looking at before, but I've just chosen the Australian ones here. Okay, so that's that one there. And just comparing those. And interestingly, here it gets a little bit confusing again, right? So just you can't say, oh, yeah, I can just look it up online and use whatever. You have to understand where these things come from. So here, right, plastic section modulus, on this website, they don't even have the standard elastic section modulus that we need for elastic beam design. And you can see here the plastic section modulus corresponds to the S table in this, the S column in this table. All right. Questions or anything coming in on the chat? No? Okay, the other thing to be aware of if you're building with wood, and there's standards for construction using wood and timber, need to be aware of whether it's dressed or actual dimensions. Okay, so the dress dimensions are actually smaller than the nominal dimensions. You just need to be aware of that. And also, what we're looking at mostly in this subject is extruded sections like this. So they're all it's all just one piece. But of course, you can build up a section using plates. So you can weld 3 plates together here to make an I-beam, or you can bolt them together. And to design these properly, you need to assess, obviously, the weld and bolt strength. So that you'll also do if you choose to do mechanical engineering students will do this in Applied Mechanics and Design B. For mechanical and mechatronics or mechatronics students, Applied Mechanics and Design B becomes an elective, or if you're from electrical or civil or biomed doing this subject, then I think you can take Applied Mechanics and Design B as well. But yeah, so that's left until that later subject. All right, so let's have a quick look at a pretty simple example. Go through the process and see how it all comes together. So we just got a fairly simple case here, just a beam with a winch, a motor and a winch sitting on top, supporting a load. And we're asked to determine the lightest wide flange W310 shape that can safely support the load. So the reason that this particular one might have been chosen, so remember this first number is the depth of the beam. So in part of your design, you know, if it's going into a roof or something, or if it's something like this where you've got it's in a workshop and you've got a crane, and this may be a gantry crane that moves along, you have a certain head height requirement, right, or a certain amount of space that you've got to fit the beam inside. So someone might have done some work previously and said, okay, the maximum depth that we can have for this beam is 310 mils. Right, so that's how that may have been chosen. And chosen to be made from steel, which is usual for this kind of a design. So, you know, given the type of steel, got an allowable stress. All right, so now we need to determine the size of beam that we want. Okay, so our solution, draw our free body diagram. apply our equations of equilibrium, calculate our reaction forces, determine the shear force and bending moment, calculate the maximum shear force and bending from our flexure equation for beam bending, determine the required section modulus, and then from a table of standard shapes, select our beam shape, check the shear stress, and then check the self-weight stress. And also, I haven't put it on this slide, but we'll check the deflection as well. All right, so drawing our free body diagram, pretty simple one in this case, so I don't have to spend too long on it. The other thing to note is this is a bit of a simplification, obviously, having a point load here. If we go back to our actual diagram, right, we've got this motor supported at 2 bolts. So, you know, there's the distributed load underneath here, there's bolt loads, etc. So a little bit more complicated than I've shown in this simplification, but we'll just work with that for now. All right, drawing our free body diagram, apply the equations of equilibrium. Some of the moments equal 0, some of the forces equal 0. And we can work out that the reaction force on the left and the reaction force on the right are both 25 kilonewtons. And then we can draw our shear force and bending moment diagram. Okay. Hopefully you can see where you've got those from, right? So if we do take a cut, if we take a cut through here, then we have a shear force in here. So that's going to be a constant shear force equal to the reaction force on the left. And we've also got a bending moment. So that will be 25x and linear. So from 0 to here, 25 times 2 is 50. Right, so hopefully you can see where this comes from easily enough. All right, so our maximum shear force is 25 kilonewtons and our maximum internal bending is 50 kilonewton meters. Okay, so from our beam flexure formula, or the rearranged version of it where we have the required section modulus, maximum bending moment over the allowable stress, so we have 50 kilonewton meters, so 50 by 10 to the 6 Newton millimeters. So 50 kilonewtons becomes 50 by 10 to the 3 newtons, and meters becomes 10 to the 3 millimeters. So that's why we have 50 by 10 to the 6 divided by our allowable stress, which was 150 megapascals, gives us a required section modulus of 333 by 10 to the 3 millimeters cubed. Right. So now if we go to our table, so we were told we wanted to use a wide flange beam with a depth of 310. So we go into here, we look for our section modulus over here, come down. So 415 is our closest one. 281 is too small, so we've got to go up to 415. Right, so we need a W310 by 33. Okay, so just put that in there. So we've got 33 kilograms per meter for the weight of this beam. I'll just put in there some of the other dimensions just for reference. All right, so now let's check the shear stress. So the maximum shear stress, VQ upon IT. Our maximum shear force was 25 by 10 to the 3. And notice we've made use of an approximation here. So in simple beam design, for an eye shape, an eye cross-section beam like this, most of the shear is carried through the web. Okay, so as an approximation or a simplification, instead of going through the full shear stress formula, you can just do the average shear stress over just the web. Okay, so the web is this vertical piece. Right, so that gives us 12.1 megapascals. As an exercise, it might be worthwhile just to revise using the VQ upon IT and see how close this is. If you want me to, at the end of this video, I might come back and do that calculation if anyone wants me to revise this shear stress formula. All right, so this is well below the allowable shear stress that we had of 85 megapascals, so that's all good. Oops, my animation's messed up there. So check the stress due to self-weight. So in everything we've done so far in this subject, we've ignored the weight of the components. Right? So let's have a look in this case and see how important it is or isn't. Right, so our weight will be a uniformly distributed load over the beam. So we've got 33 kilograms per metre, so multiplied by 9.8 metres per second squared gravity to get to newtons. So we have approximately 330 newtons per metre, or 0.33 kilonewtons per metre. Right, so that's our weight, and right, already you can hopefully see that it's going to be pretty small, right? Remember what our point load was? It was 50 kilonewtons. Right? So this is going to be not very much at all. But anyway, let's do the calcs and see what we get. All right, so working out our reaction forces from our equations of equilibrium, calculate M max. So I've just gone through that. Taking a cut through here. The maximum will occur at the middle or the center of the beam. So M max is 660 Newton meters. Right. What did we have before? I can't remember. It was way bigger than this. It was kilonewtons per meter. So the normal stress using our beam section that we've just, our section modulus that we've just got from the table. Right. So now we use the actual section modulus, 415, that we got from the table, right? Here. Right. Use this value, not the 333, because now we have an actual beam that we're making use of. Right, so you can see that the stress due to the weight of the beam is negligible. And also we've chosen a beam with a 26% larger section modulus than was required. So the calculations said we need 333.33. We used a beam with section modulus of 415. So no worries about ignoring the weight. Then check deflection. This is the loading that we have. If you want to include the self-weight, you probably don't need to. It's going to be negligible, but let's put it in just for the sake of the exercise. So the weight was, self-weight was 330 newtons per metre. Our working load was 50 kilonewtons. Calculate the maximum deflection. So let's not use the integration method. It's too much work. Let's look up the deflection from our standard beam slopes and deflections table. So we've got load at the center. So maximum deflection from that point load is PL cubed upon 48 EI. And from the distributed load, it's 5 WL to the fourth on 384 EI. So we can add those together from superposition. Right, total length is 4. Young's modulus of steel is 200 gigapascals. Moment of inertia we need from our table. So if we go back to where we selected this, right, here's our moment of inertia about the x-axis. So make sure you choose the right one. So 65 by 10 to the 6 millimeters to the fourth. Right, so that's where that numbers come from. Draw the values in and we get a deflection of 5.2 millimeters. Then what? Is that good? Is that bad? Right, so you need some kind of requirement to be able to judge whether this is acceptable or not, right? So one way to judge this is to look at, that there's kind of a range of deflections depending on the application. So this one I've got from this Machine Elements in Mechanical Design textbook. So a recommended deflection limit for just a general machine part is, if your deflection somewhere between 0.0005 to 0.003 millimeters per millimeter of beam length, then that should be okay. For precision machine parts, then that requirement will be tighter, but assume this is just a general requirement. So from our calculations, we've got 5.2 millimeters deflection in 4 meters or 4,000 millimeters. That gives us 0.0013, which is less than 0.003. So, okay. All right. And then, so now I've just had a look at, so we chose a beam from the textbook list of W flange beams. Let's choose one from One Steel. So our requirement was 333.33 by 10 to the 3 millimeters cubed. So let's see what we can find down here. So I think we're looking for a 310. It was 310, wasn't it? Pretty sure it was 310. So 310 UB. Down here we've got maybe not. Yeah, they're all too big. What do I choose? 354. Okay, this one down here. Right. So shows one that's even smaller depth. Right? A little bit less weight. And remembering that we need to choose this column, the Z column in this table, because they've messed up. Well, haven't messed up, I guess, but they've used Z for the section modulus rather than S. Right, so we could have chosen this beam from One Steel and that would have been okay. All right, so to sum all that up, so draw your free body diagrams, use your equations of equilibrium to determine your support reactions, determine your shear force and bending moment diagrams, calculate the maximum shear and the maximum bending, specify a material, and that gives you the allowable stress. From that, you can calculate your required section modulus, select your beam, check the shear stress, check the self-weight, check the deflection. And if you're doing this in practice, in industry, for a real structural application like a crane or something like that, then make sure you comply with the relevant standards or codes such as AS4100. All right, so that's it for that. And you can see that this here, is really in many ways a summary of the whole subject. So we started off at the start of the subject, drawing free body diagrams and applying equations of equilibrium. And then we've worked through all of this stuff each week throughout the subject.